So, hey everyone, how are you guys doing today? Today we're going to move into chapter 5, which is all about conditionals and recursion. In the last couple of chapters, I'm just going to look up these things. We went through some super basic stuff, introductions to functions, variables and statements, typings. Um, uh, we dabbled a little bit into something that is an important concept in the last episode of interfaces, where interfaces are um, every function that you make that you call essentially has an interface. It requires you to pass arguments in a certain way to it, and then it'll do its job, right? And keeping these two different things different, the interface, aka how you call a function, I'm encapsulating this conversation in the context of functions because if you are really beginning, this is important to understand. Um, that this doesn't apply just to functions, but I'm just going to use that because you already understand functions because we've been introduced to it. Um, the capability to conceptually split those two in your head. Implementation is different from interface. How you call the function is different from the function itself. Uh, it really opens up a whole world. There's loads of concepts that exist that are like this, right? That are extremely interrelated, but specifically distinct things, right? Because in in computer science, with a lot of these things, um, you don't in computer science with a lot of these things you don't need you if you understand these concepts and abstractions. Many times there is a programmatic effect in the sense that there will be a concept or a feature of languages that you can utilize to do something with this concept materialistically rather than just help you out mentally, right? And so if you can kind of be comfortable in thinking abstractly and accepting things conceptually and trying to be like, I'm in a whole new world, I don't exist on planet earth, and these are the rules of this world, right? And I have to pretend like I know nothing. And kind of think in that framework conceptually. That'll help a lot because a lot of these concepts are formalized with language features and capabilities and like other things that it's even hard to describe regarding deployment and how things work in a professional environment. So moving back to chapter 5. And chapter 5 is about conditionals and recursion. Recursion is one of those things, and they actually mention it here. We'll be able to explore one of the most powerful ideas in computing, recursion, which actually, yes, it is one of the most powerful ideas in computing, but actually you don't use it that much. So it's like, I, it's weird chicken and egg thing where you need to understand it, what it does and how you could use it to become a good software engineer because it helps you think in that abstract way like I just described. Like if you can get this, like a lot of things like snap into place conceptually. But at the same time, it is quite rare for someone to be writing recursive code in a production environment. In fact, you want to avoid recursion as much as possible because it's not exactly efficient, right? 90% of most people's work is to avoid repetition, right? Um, anyways, but it is one of the most powerful statements, and I think in this chapter we're getting into the if statement and how that ties into recursion because there's like the thing about base cases and stuff like that. And recursion is a thing in math as well, by the way. So if you get it in math as well, it still works. Integer division and modulus. Recall that the integer division operator divides two numbers and rounds down to an integer. For example, suppose the runtime of a movie is 105 minutes. I'm gonna pause recording. Hey, sorry about that, guys. There's a bit of an interruption. I got distracted in my head regarding something. I'm gonna move this over here. Conditionals and wait, no, we already talked about conditionals and recursion. And we're also going to start with modulus operator, Boolean expressions, and logical operators. So integer division and modulus. So recall that the integer division operator // divides two numbers and rounds down to an integer. For example, suppose the runtime of a movie is 105 minutes. You might want to know how long that is in hours. Conventional division returns a floating point error. Why? Oh, returns a floating point number, not error. I read this as conventional division returns a floating point error. I'm like, what? Why? Yeah, it returns a floating point number, so 1.75 hours, but we don't normally write hours with decimal points. Integer division returns the integer number of hours, rounding down. So hours equals minutes divided by 60, but that's 1 hour, and 105 minutes is like closer to 2. It's like an hour and 40 minutes, 45 minutes. To get the remainder, you could subtract for 1 hour in minutes. Yep, so right there. So you get the 45 minutes. Or you could use the modulus operator, which divides two numbers and returns the remainder. So yeah, so basically 105 divided by 60. 60 goes into 105 once, right? And then whatever the remainder of the past is. But that would still be true. So if it's 135, for example, here, I'll just show it to you. 135 would be 15, because 60 would go into 120 twice, and then you would have, so 120 plus 15, which is 135, so this should be 15, and boom, it's 15. I'm just gonna showcase that to you. So that's what the modulus operator does. It comes in handy here and there. Modulus operator is more useful than it might seem. For example, it can check whether one number is divisible by another. If x over y is 0, then x is divisible by y. Yeah, that's like a very simple arbitrary one, but there's many other non-mathematical ones that it is useful for as well. Also, it can extract the rightmost digit or digits from a number. For example, x modulo 10 yields the rightmost digit of x in base 10. Similarly, x modulo 100 yields the last two digits, right? So yeah, this would be like 3, this would get you 3, this would get you 23, etc., etc. So that's what this is saying. Finally, the modulus operator can do clock arithmetic. For example, if an event starts at 11 a.m. and lasts 3 hours, we can use the modulus operator to figure out what time it ends. Start 11, duration 3, start plus duration modulo 12. Yeah, start plus duration modulo 12, right? Because, because 11 plus 3 is 13. And you want to know when it ends, so you divide by 12. Yeah, modulo 12. It's just like a quick way to do that. Boolean expressions. So this one's important. When you do equals, it's considered a Boolean expression, not an assignment, which is the single equals operator. And what that means is it's checking whether something on the left and something on the right are equal to each other, right? It's an expression that is either true or false, right? So this is an expression that once it's evaluated, it returns either true or false, right? It'll return one of those two things. For example, the following expressions uses the equals operator, which compares two values and produces true if they are equal and false otherwise. So it's 5 equals 5. That'll be true. And then 5 equals 7 is false. A common error is to use a single equals sign instead of double equals sign. Remember that equals assigns a value to a variable, and equals compares two values. So yeah, that's an important one. I just mentioned that. So here we're assigning, we can also do Boolean operators with variables, basically. And true and false are special values that belong to the type bool. They are not strings. So yeah, you can check that out here. Bool for Boolean. I wonder what is the origin of the word Boolean, because that is true in many language. is Belowism. Originates from 19th century English mathematician George Boole, who developed mathematical logic and what is now known as Boolean algebra. His work established an algebraic system for representing true and false values, which is fundamental to computer science and the basis for the Boolean. Okay, so it was named after a guy. I'm just going to run that again so I can... There you go. I just wanted that thing to disappear. So type of true and type of false, and these are also true and false. The capitalized true, capitalized false, those are accurate. Those are reserved keywords. True and false are reserved keywords. Equals equals operator is one of the relational operators. The others are x exclamation point equals y, so that's x is not equal to y, x greater than y, x less than y, x greater than equal to y, or x less than equal to y. I'm just going to run all of these. Less than y, and yeah. So I don't remember what x, I think it's 5 and 7. So this is true and this is true, and the rest should be false. Yeah, and x not equals y, so they're not equal to each other. That's also true, and these two should be false, which they are. Logical operators. To combine Boolean values into expressions, we can use logical operators. The most common are and, or, and not. The meaning of these operators is similar to their meaning in English. For example, the value of the following expressions is true only if x is greater than 0 and less than 10. Right, so x greater than 0 and x less than 10. True. Yeah, because x is 5, I believe. You can also do that with other expressions and things like that. So if the number is divisible by 2 or 3, because x modulo 2 tells you whether it's divisible by 2 if you get 0. If either of these are true, it'll be true, and it's not because x is 5. The not operator negates a Boolean. So the following expression, if true, x greater than y, is true if x greater than y is false, right? So if this is false, so not just negates it. Whatever is false becomes true, whatever is true becomes false. Right, there's just I'm sure there's like a little handy table you could look up with logical operators. 42 and true. Strictly speaking, the operands of a logical operator should be Boolean expressions, but Python is not very strict. Any non-zero number is interpreted as true. Yes, that is correct. And also there's other things. So if you check a list, and if that list is empty, it'll evaluate as false, but any items in the list will evaluate as true, right? So if list, then do something, right? For example, if you initiate a list and certain items are meant to be collected into that, and there's some code to be run, if those items are in that list, you can just go if list and run that code. So yeah, that is true, and like that's just essentially helps writing things in a Pythonic way, but it also means that there is essentially a truthiness to things, right? Things other than Boolean values can have a truthiness or a falsiness to it, which is evaluated into a Boolean of true or false by Python dynamically at runtime. This flexibility can be used, but there are some subtleties to it that can be confusing. You might want to avoid it. Yeah, definitely. I agree with that sentiment. You don't want to use this generically. You have to use it very specifically. Like the if list thing is a very common one. And there's a few other things tied to this truthiness and falsiness in Python that is helpful, but that's the only way you should be doing it. You should never explicitly compare something that is meant to evaluate as a Boolean with something else that's not. You shouldn't be doing that directly. Just utilizing the concept to make more succinct code. If statements. In order to write useful programs, we almost always need the ability to check conditions and change the behavior of the program. Accordingly, conditional statements gives us this ability. The simplest form is the if statement. If x greater than 0, print x is positive. If is a Python keyword. If statements have the same structure as function definitions, a header followed by an indented statement or sequence of statements called a block. Oops. I didn't mean to do that. If it's a Python keyword, if statements have the same structure as function definitions, a header followed by an indented statement or sequence of statements called a block. Yeah, block of code. The Boolean expression after if is called the condition. If it is true, the statements in the indented block run. If not, they don't. There is no limit to the number of statements that can appear in the block, but there has to be at least one. Occasionally, it is useful to have a block that does nothing, usually as a placekeeper for code you haven't written yet. In that case, you can use the pass statement, which does nothing right here. So if you do this, prints x is positive. If x is negative, it does nothing. So yeah, it's exactly what it is. It's as a placeholder for code you haven't written yet. The word to do in a comment is a conventional reminder that there's something you need to do later. Yeah, so that's true. The else clause. An if statement can have a second part called an else clause. The syntax looks like this. If x modulo 2 equals 0, print x is even, else print x is odd. If the condition is true, the first indented statement runs, otherwise the second indented statement runs. In this example, if x is even, the remainder when x is divided by 2 is 0. So the condition is true and the program displays x is even. If x is odd, the remainder is 1, so the condition is false and the program displays x is odd. So yeah, this is essentially exactly what this does. This checks if x is even, right? If it's divisible by 2, aka if its modulo is 0 when divided by 2, you print x is even, otherwise you print x is odd, and that's that. Chained conditional. Sometimes there are more than 2 possibilities and we need more than 2 branches. One way to express a computation like that is a chained conditional, which includes an elif clause. So if x less than y, print x is less than y, elif x greater than y, print x is greater than y, else print x and y are equal, right? So yeah, you can add more than just if and else. You can do elif to add more. Personally, I don't like if, elif, else. I think just if, because in many situations you can remove the else, or the elif, but I'm not, this is me being biased, right? It's whatever. Elif is an abbreviation of else if. There is no limit on the number of elif clauses. If there is an else clause, it has to be at the end, but there doesn't have to be one. Each condition is checked in order. If the first is false, the next is checked, and so on. If one of them is true, then the corresponding branch runs and the if statement ends. Even if more than one condition is true, only the first true branch runs. Nested conditionals. One conditional can be nested within another. You could have written the example in the previous section like this. If x equals y, print x and y are equal. Else if x less than y, x is less than y, else x greater than y. Yes, so you can nest things within each other, right? Like how you could put a loop inside a function. You could put a conditional inside a loop inside a function. You can, like, anything can have anything. Yeah. The outer if statement contains 2 branches. The first branch contains a simple statement. The second branch contains another if statement, which has 2 branches of its own. These 2 branches are both simple statements, although they could have been conditional statements as well. Yeah, so logical operators often provide a way to simplify nested conditional statements. Here's an example with a nested conditional. If 0 less than x, if x less than 10, print x is a positive sign. If 0 less than x and x less than 10, print x is. So yeah, that's essentially what logical operators do. Helps with succinctness, but also it helps with succinctness, but also it helps with readability, right? If you're doing if, like, that's harder to see, like if this and this. And it aids with like much more complex logic operations being chained together, which, and honestly, if it gets super bad, you would want to do nested and that, but like ideally you would not want to do that. If x is between 0 and 10, print x is a positive single digit number. Recursion. It's legal for a function to call itself. It may not be obvious why this is a good thing, but it turns out to be one of the most magical things a program can do. Here's an example. Countdown. If n less than equals 0, print blast off, else print n countdown n minus 1, right? So basically this function, when you call it the first time, you say you call it with 10, right? If n less than equals 0, print blast off. Okay, so it's not less than or equal to 0. So because n is 10, then just prints 10 and then calls itself again and subtracts a number. So it becomes n. So this execution will then go back into the function with n9 and it just keeps calling itself again and again until the last one when it's 0, when it goes to blast off, which then the blast off, when you finally do blast off, that is actually the end of the recursion, and that returns to the previous calling function, right? Which would be a countdown where n was called with 1, then countdown n2. So it like returns to the previous function call, which ties into the concept of stacks from a couple of episodes ago. So if you just run countdown, I didn't run this, I gotta run this first, then I gotta run this. If n is 0, negative countdown outputs the word blast off, otherwise it outputs n and then calls itself passing n minus 1. Here's what happens when you call this function with the argument 3. I'm just gonna run that again, second. That's like a weird bug where sometimes the thing lasts longer than it needs to. The execution begins with n equals 3, and since n is greater than 0, it displays 3 and then calls itself. So execution of count. So it's just describing what I just described with indentation. The execution of countdown begins with n equals 1. It displays 1 and then calls itself. And the execution of countdown begins when n equals 0, and since n is not greater than 0, it displays blast off and returns. Countdown that got n equals 1 returns. Countdown that got n equals 2 returns, and so on and so forth. And then it's done, right? So this is the stack, essentially. The calling stack. A function that calls itself is recursive. As another example, we can write a function that prints a string n times. If n greater than 0, print string, print n times string n minus 1. Yeah, I mean, this is an arbitrary example that you could have rewritten as a for loop, but yes, this is also just calling itself. If n is positive, print n times, displays the value of the string, and then calls itself, passing along string, and n minus 1 as arguments. If n is 0 or negative, the condition is false, and print n times does nothing. Here's how it works. Here's how it works. Print n times spam. For simple examples like this, it is probably easier to use a for loop, but we will see examples later that are hard to write with a for loop and easier to write with recursion, so it is good to start early. So this is basically saying what I said, that this is a fairly arbitrary example because this could have been rewritten as a for loop, but with certain other types of things, that's not necessarily the case. So stack diagrams for recursive functions. Maybe I didn't run the first thing. I'm just going to run that again. And then come back down here. Run this and this, because this is just showing me the stack diagram. So countdown, countdown, countdown. 4 countdown frames have different values for parameter n. The bottom of the stack, where n equals 0, is called the base case. It does not make a recursive call, so there are no more frames, right? And then print n times is just string hello, hello, hello with different n again and again. That's the stack. Infinite recursion. So if recursion never reaches base case, it goes on making recursive calls forever, and the program that this is known as infinite recursion is generally not a good idea. Here's a minimal function with an infinite recursion. Now, I'm dead certain that this will run for a moment and then it'll be like max iterations exceeded or something like that in a moment. Let's see. Oh, why did that not happen? Okay, because you have to actually call recurse. Recurse is called, it calls itself, it creates another frame. In Python, there's a limit to the number of frames that can be on the stack at the same time. If program exceeds the limit, it causes a runtime error. Maximum recursion depth exceeded. Yeah, so that's exactly what happens. That's when you just, and that's where you have the term stack overflow. That's another way to have a stack overflow error. Anyways, the traceback indicates that there were almost 3,000 frames on the stack where the error occurred. If you encounter an infinite recursion by accident, review your function and confirm that there is a base case that does not make a recursive call. And if there is a base case, check whether you are guaranteed to reach it. The programs we have written so far accept no input from the user. They just do the same thing every time. Python provides a built-in function called input that stops the program and waits for the user to type something. When the user presses return to enter, the program resumes and input returns what the user typed as a string. Okay, so this is just talking about the input function, literally just taking in some input, right? I don't understand why it says solution goes here. Getting input from the user, you might want to display a prompt telling the user what type input can take a prompt as an argument. Bitches. Nah. V. I'm just gonna go with V. Yeah. So this is just an argument to the function input. Sequence /n at the end of the prompt represents a new line, which is a special character that causes a line break. That way the user's input appears below the prompt. If you expect the user to type an integer, you can use the int function to convert the return value to int. Yeah, so I could do, so this won't have value error, but if I put in something else, that will, right? Invalid literal for int with base 10, yeah, definitely. Very basic thing. So this is basically a function that allows you to take input from the user. Pretty straightforward. Debugging, so indentation error, so this is irritating. Syntax errors are usually easy to find, but there are a few gotchas. Errors related to spaces and tabs can be tricky because they are invisible and we're used to ignoring them. Yeah, so this is an indentation error. I don't know what else is trying to say, but can we? Yeah, so this is true, what kind of error it was and where it occurred. And if you have like a stack trace, seeing the topmost or the lastmost error, sometimes it prints it in awkward ways, is the one you need to fix, and everything else is like, whatever. Problem is that the second line is indented by one space, but the error message points to Y, which is misleading. Error messages indicate where the problem was discovered, but the actual error might be earlier in the code. The same is true of runtime errors. For example, suppose you're trying to convert a ratio to decibels like this. Decibels equals 10 times log 10 ratio. Yeah, I see, because this is a floor division, so this will be 0, and so it's discovered on decibels when you call math log 10 with ratio 0. But you know, the issue is before that, where you calculate. The error message indicates line 5, but there's nothing wrong with that line. The problem is line 4, which uses the integer division instead of floor. So the value of ratio is 0. When we call math log 10, we get a value error with the message math domain error, because 0 is not in the domain of valid arguments for math log 10, because the logarithm of 0 is undefined. In general, you should take the time to read error messages carefully, but don't assume that everything they say is correct. Yeah, so that's all 100% true about errors. Like, you need to be a bit careful. This is a glossary. Once again, I love their glossary. It's like really neat. I feel like you could just go through the glossary, and if you understood all the words, you do really well. Some exercises here. Let's see what's going on. Ask conversion. What are some use the modulus operator? Nope, I'm not asking that, but it is very useful, and you could look that up. Python provides operators to compute logical operators and or not, but doesn't have the operator that computes the exclusive OR operation, usually written with XOR. Asking this was a logical XOR operation, and how do I compute it in Python? I'm just gonna ask, how do you use XOR in Python? I know there's the bitwise XOR. No, I don't want the bitwise. Yeah, so you could just write your own function, basically. Makes sense. In this chapter, we saw two ways to write an if statement with 3 branches. Using a chained conditional or a nested conditional, you can use a virtual assistant to convert from one to the other. For example, ask a VA to convert the statement to a chained conditional: x equals 5, y equals 7. Do it like this. Ask a VA to rewrite the statement with a single conditional, so you can just do this and see if a VA can simplify the unnecessary complexity. If not x less than equals 0 and not x greater than equal to 10, x is a positive single digit number, you could just remove the not and say x greater than equals 0 or x less than 10, you know, and x less than 10, sorry, not or. Here's an attempt to recursive function that comes down by 2. Seems to work, but it has an error. Ask virtual assistant what's wrong and how to fix base the solution. If it provides, back here and test it. Yeah. The time module provides a function also called time that returns number of seconds since the Unix epoch, which is January 1st, 1970, blah, blah, blah. From time, import time now equals time. Okay. Use integer division in the module sort to compute the number of days since January 1st and the current time of day and hours. Yeah, okay, I'm not doing that. If you are given 3 sticks, you may or may not be able to arrange them in a triangle. For example, if one stick is 12 inches long and the other 2 are 1 inch long, you'll not be able to get the short sticks to meet in the middle for any 3 lengths. This tests if any of the 3 lengths is greater than the sum of the other 2. Otherwise, you can. If is triangle that takes 3 integers as arguments and that prints either yes or no, depending on whether or not you can form a triangle from sticks with the given lengths. Hint: use a chain conditional. Okay, yeah, that's it's I think that's something to do with Pythagoras. Essentially, it's the triangle inequality. You can't have one side that is greater than the other 2 sides combined, or something like that. Is triangle. Yeah. What is the output of the following program? Draw a stack diagram that shows the state of the program when it prints the result. Following exercise uses the Jupyter Turtle module described in chapter 4. I don't know what a Koch curve is. Know about the functions, but there are many versions with different names, so VA may not know which to solve when you can provide problems here. And then paste in one of the examples from the chapter. After that, the VA should be able to generate code that uses this module. Let's go VA for a program that shows Sierpinski's triangle. Okay, so like a bunch of triangles, more playing around, using conditionals, maybe using recursion. I'm not going to do any of those exercises, though they do actually seem kind of fun. Like now I'm like, that's kind of stuff like I do want to do. It seems interesting. Like, oh, how would you do this? Just like as a fun coding exercise. And yeah. Good chapter, important stuff. I'm going to move on. I think I'm doing this more as a conceptual overview. Maybe I'll come back to the exercises, but I mostly want to actually speed through this book for someone else's sake, and so I just want to read it rather than solve it. Yeah, so I'm just trying to zerg this down as fast as possible. Thank you guys for listening, and I'm going to move on to the next video. Catch you guys later. Have a good one.